Hi everyone. So in this video, we're going to do a DC analysis of this common source self-biased amplifier. So the active device here is an N-channel JFET. So what we're going to do is we're going to figure out the expressions for VGS, that's the gate to source voltage, VDS, the drain to source voltage, ID, that's the drain current, and then VD, VG, VS, that's the terminal voltages, if you like, of the drain, the gate, and the source, respectively. And we're going to figure all this out at the Q point. The Q point, if you guys remember, is the quiescent point or the quiet point when there are no signals coming in. So the idea is to figure out, how to bias this device so that the amplifier will function the way that we want it to. Okay. All right. So as usual, whenever we're doing a DC analysis, we have to do a few steps. The first one is to open all capacitors because the impedance of capacitors at 0 hertz, right, at DC voltages, 0 hertz is infinite. Because why? Impedance of capacitors 1 over j omega c, and omega is 2 pi f, and f is 0 hertz. So therefore, 1 over j omega c becomes 1 over 0. So that's infinite impedance. Okay. And then we remove all signal sources and we figure out based on different components of currents and voltages to figure out what we need to know. All right. So the first thing is to look at the circuit without, with the C1 and C2 open circuited. So what you have is just the middle part of the original circuit with C1 and C2 cutting off both VI and VO. All right. So next, let's label all the currents and voltages that we're interested in. So first one is this current that goes through RD. Okay, it goes through RD. So I call it IRD. The current that goes through into the drain, I call that ID. All right, so that's ID going into the drain. The current comes out of the source. Obviously, I'm going to call that IS for source current. And then the current that goes through IRS. Okay, so call it IRS. And then of course the current that goes to the gate, which for an FET device is always going to be 0. All right, because of the way that the FET is constructed. All right, so IG that's flowing into the gate is going to be 0, 0 amps. Okay, so 0 amps there. Sorry, let me just put this down a bit. Okay, all right. Now for voltages, the voltage across RD, I'm going to call it, VRD. What else? The voltage across drain and source, I'm going to call that VDS. So let me just put this out a bit. Okay. And finally, the voltage across RS, I'm going to call it obviously VRS. And last but not least, VGS, that's the voltage between gate and source, the one that we're interested in. So we're interested in VDS, VGS, VD, VG, and VS. All right, so let's write some expressions for some of those components. So the first one is, the first one is always this right-hand side, the drain current, the source current, and then IRD and IRS. If you notice, since there's no current going into the device via the gate, therefore whatever goes into the drain will come out of the source. So that means all 4 of these current components are the same: ID, IS, IRD, and IRS. So let's write that down first. So ID is equal to IS, and that's equal to IRS, and that's equal to IRD. All right. And what is the expression for ID? Well, for a JFET device, this is the expression for ID. ID is equal to IDSS times 1 minus VGS over VP all squared, where ID is the drain current, IDSS is the saturated drain source current, VP is the pinch-off voltage, and VGS is the gate source voltage. So typically, when we're dealing with Q point, some people use IDQ is equal to IDSS 1 minus VGS Q divided by VP all squared, right? Q being the Q point. Okay, so let's have a look at the voltages side. Okay, So I'm just going to continue here. So, well, let's have a look at VRD. Oh, sorry, let me just write down for completion's sake what is IG. So IG is going to be 0 amps. That's all it is, right? Okay, so that's the IG side. So that's all the current side of it. So let's have a look at the voltage side. Well, what is VRD? Well, VRD is the voltage across RD, and that's just going to be Ohm's law. So it's going to be IRD times RD, right? So, but I'm just going to write as well. Okay, let's just write that down. RD, and since IRD is ID, so therefore it's just ID times RD. Okay. And similarly for VRS, VRS is equal to IRS times RS, which is equals to ID times RS. Okay, so that's VRD and VRS. Okay, so now let's have a look at the terminal voltages of the active device. So let's start with VD. Okay, what is VD? Well, VD is the drain voltage from the drain terminal all the way to ground. All right, so we can look at this as using KVL. VDD is from all the way to the top to the bottom. So you can say that VD is equal to VDD minus VRD, right? So then you'll get an expression for VD. Or another way, you could say that VD is equal to VDS plus VRS. So that's also another way. But then I don't have an expression for VDS yet. So I'm going to use VDD minus VRD. Okay, so and we know what VRD is. That's just IDRD. Okay, now let's have a look at VS, the source voltage with respect to ground. Well, VS is from the source to ground, which is just equal to VRS. So that's just equal to VRS. All right, and we know the expression for VRS, which is IDRS. Okay, and finally for VG, let me space this out a bit. Okay, so what is VG? Well, VG is the gate voltage from the gate to ground, but then because there's no current going through the entire path, that means the voltage drop across RG is going to be 0 volts, meaning that VG is 0 volts. All right, so fairly straightforward. So now let's have a look at the individual, the other two components that we're interested in, VGS and VDS. Let's start with VGS. So VGS is equal to just simply, you can write as VG minus VS. Right, and we know VG is 0, so this is 0 minus VS, and we know that VS is just IDRS, and therefore it's just negative IDRS. Okay, so that's VGS. And then finally for VDS, it's simply VD minus VS. And we have expressions for those. VD is VDD minus IDRD. And then, okay, let me just put in brackets just to be a bit explicit. Minus VS. Well, VS is just here, IDRS, right? So IDRS. So we can combine IDs together. So then what you're left with is just VDD minus ID multiplied by RD plus RS, right? Okay. So those are that's the expression for VGS and expression for VDS. Now I want to relate this to the input and output characteristics of a JFET, for example, in this case. And before we do that, let's turn these two equations into a form of y equals mx plus c. Okay, so basically, in an input characteristic curve, the vertical axis is ID, and the horizontal axis is VGS. For output characteristics, vertical is ID, horizontal is VDS. So basically, it's just this equation here. I just manipulate it so it becomes, so ID becomes the subject matter. So therefore, ID is equal to negative VGS over RS. And similarly for the expression for VDS here, right? I just make ID the subject of interest, so then you get this expression. All right, okay. So in terms of y equals mx plus c, that's the y. So the IDs of the y's. The x for the input characteristics, that's VGS. The x for the output characteristics is VDS. And the m, the gradient, in the case of input characteristics, is -1 over RS. And for the output characteristics, m, the gradient, is -1 over RD plus RS. C would be 0 for the input characteristic line, and C would be this expression for the output characteristic line. So in terms of plotting it on both the input and output characteristic curve, you'll see that this is the load line of ID equals negative VGS over RS, right? So where the gradient is dependent on RS, right? So dependent on RS. And then for the output characteristic curve, again, a load line that is this equation here. That's the load line with that equation. Where it crosses the vertical axis, that just means that VDS is equals to 0. So if you look at this, you make that 0, then ID is simply equals to this. That's what that is. And then when you want ID equals 0, then the only way it can be 0 is if VDS is equal to VDD, because the bottom part are the same. So that's where you get VDS equals VDD there. Okay, so those are two load lines. And typically in amplifier design, we figure out what these values are in order to get a particular kind of load line, because we want a particular kind of output when we're amplifying our signals. All right, so I hope that's been useful. Thanks for watching. See you guys in the next video. Bye.